very pleasure to have Pasha Zusmanovich, our first speaker of this seminar of this year. So Pasha already visit Prague many times and give a talk.
Yeah, in the past, yeah.
Yeah, in our seminar before the COVID. And now that kind of the COVID approach to the end, and you visit us again and give a lecture on algebra in characteristic 2. Yeah.
Okay.
I don't hold. Oh, I see. So I don't hold all the time. Yeah. Okay. So now it's. Okay. So.
Yeah.
Please.
Okay. So thanks. All right. Okay. So thank you very much. Thank you, Van. It's so indeed like it's actually it was almost my first talk in this this work which trying to return to normal. Yeah. So now we have this hybrid word. All right. So yeah, Lie algebra characteristic 2.
We have some question on the chat.
And yeah. Okay. Well, and yeah, it's like written. It is written. It's based on work which appeared recently. Several co-authors. All right. So it's about. So what is the main context? Yeah. So we're trying to classify simple algebras in characteristic 2. So what? It should be all right. Thank you. A simple algebra characteristic 2, which in a sense it's very natural question. Yeah. So we have some class of algebraic objects, and we want to classify them, and we cannot. Yeah, and to classify simple objects and something else. So simple algebras. Yeah, it's everybody knows. It's classical piece of mathematics. Killing Katan Dinkin probably was the last who put this final touch with Dinkin diagrams in the 30s. And then, okay, people classified algebras in positive characteristic, which took somewhat longer. So basically, it started more or less like at the same time, probably when with this final touch in zero characteristic.
That's the touch.
All right.
I'm sorry.
Okay.
Mute yourself, please.
One, you can return. Okay, so I continue. So basically, in characteristic 3, the activity started probably around the same time, coincidentally, when this final touch in characteristic 0 were done. Work of Witt, probably the first. He constructed the first example, what's nowadays called Witt algebras. In 39, I think, like that, before Second World War. And okay, so some first examples, and then people tried to think how to, and it was clear more or less, maybe not immediately, I think, yeah, because those examples of Witt and first algebra and positive characteristic, they were very different, yeah. From characteristic 0, it was clear that the situation sounds somehow much more complicated, and at certain point, it was not clear that it is possible to do at all. Yeah, in 50s, people, meaning new examples of simple algebras emerged. Okay, of course, we're talking about finite dimensional, and it was like some zoo of different examples, and even some people expressed like sort of doubt that it's possible at all. Jacobson, yeah, the classic he said that probably it's impossible to classify simple algebras as positive. Of course, yeah, some finite dimension over algebraically closed field, yeah. Over non-algebraically closed field is another story. First, we should deal with algebraically closed field, and then maybe consider forms, which is it's another story. Yeah, cohomology and so on. But yeah.
Question. So this classification of simple Lie algebras in positive characteristic, is it in somehow parallel to classification of finite simple groups?
Yes, it is.
Yes.
Okay. So
okay.
What is parallel? Meaning, okay. So we tell more or less the whole story, and then yes, there are many similarities. What is parallel is, but there are many similarities. So, at certain point, people were sort of, meaning it was not clear how to proceed, it seems, but then came Kostrikin and Shafarevich, basically with some, now it looked not very surprising, yeah, but inside nothing is very surprising. So they just observed. Well, they did several things, yeah, but the main thing they observed that all those new, meaning maybe not all, but some key examples like weak algebra and some generalization and so on, they actually counterparts of infinite dimensional algebras, Cartan, yeah, which were known a long time from the beginning of 20th century, yeah, of vector fields. Okay, we don't have maybe some formal vector fields or no positive what it is, what it's going to be called, yeah, but actually they're quite similar, yeah. So if you think, for example, instead of vector fields, some polynomial, some I don't know, some derivation or some operator of polynomial algebras. So instead of polynomials, you take some finite dimensional quotients, reduced polynomials, yeah, and basically they observed that and they developed some program, yeah. Then the conjecture was more or less okay. It was later it was a little bit modified, it made more precise, but actually it was that simple algebras are like that. It's a classical, like an heuristic zero, which is almost the same. Again, there's always some subtleties, yeah. There is like matrices, and the order of matrices divided by p by heuristic of the main field. There is some, but basically it's more or less clear. It's what the algebras of classical type, and then the algebras of Cartan type. You know, Cartan with this infinite dimensional algebra, and then it was wrote, yeah, to move on, and actually with some modifications, with some, and actually at a certain moment, yeah. For example, in heuristic 5, yeah, the new family emerged, yeah. It's always, I think it's not the thing, it's the fact, yeah, it's a common phenomenon. If you have some object defined over field characteristic, yeah, it can be algebras, it can be algebraic groups, it can be something more complicated, schemes, whatever, yeah, defined over a field, then heuristic, positive heuristic is usual. In almost all the cases, yeah, it's more complicated, or something much more complicated, and small heuristic, they are more complicated than some generic case, yeah. The smaller the heuristic, the more problems, yeah, the more, but basically it's like that. So there is some generic case, yeah. For the generic case, it's meaning it's ad hoc, yeah. Depends. I don't know philosophical explanation. So in this case, it's like the generic case started from 5. Actually, it's also maybe not entirely true, yeah, because at a certain point there's some proofs they assume the greater than 11, say, yeah, and then they made additional efforts to include 11 and 7, yeah, and in 5, at a certain point there was discovered a whole new class of so-called Millikan algebras. Like Millikan, there was a student of Kostrikin, and they discovered that there are algebras which are not classical, not of Cartan type, yeah, which is different, meaning, well, to define them, it takes some effort, yeah. It's not obvious. There are different realizations, yeah, but actually even define all these algebras not properly with all possible, you know, modifications and iterations, and it takes some time, it takes some effort, yeah. This is some, yeah.
I missed something because
Yeah, sure.
But
Yeah.
just what is the main difficulty when you consider the characteristic?
Yeah, it's a philosophical question. I don't know what to tell. Yeah, because it's some basics. Almost everything breaks. Yeah, some, you know, the basic theorems in the algebra theory, like, I don't know, criterion for simplicity. You have, for example, simple algebras. Semisimple algebras, a direct sum of simples. This is because all representations are finite dimensional, of course, are completely reducible, and this is because actually, I cannot just answer in give a short answer. Yeah, something when basically, okay, so very something pedestrian, but to give you basically, when you consider matrices, some representation matrices, if the order of matrices is divided by characteristic, basically you can have matrices of tray, meaning it can be it can be trace 0, but you have unit matrix, yeah, it has trace 0, something like that. Yeah, and yeah, but otherwise, meaning you start to look and you see the things, they don't work. Yeah, they don't work. For example, the structure of semisimple algebras, it's known. Yeah, it's one of those works, yeah, which we contributed to this specification. It's much more complicated than simples. Yeah, so semisimple algebras direct sum simples in heuristic 0. In heuristic P, it's of course every direct sum of simples is semisimple, but you have some constructions which actually some of them we will consider. Yeah, meaning the typical. It's some tensor products of simple algebra on something polynomial-like or reduced polynomial, plus some tail of derivations which act on this polynomial algebra, which actually make it semisimple. And semisimplicity you define in terms of that, meaning it boils down to the condition that this polynomial-like algebra doesn't have invariant ideals with respect to stable with respect to this derivation. Something like that. Actually, it's a little bit more complicated, yeah, because again, it's technical, yeah. In a sense, it's somehow it is very similar, yeah, to classification of finite groups, yeah. A lot of technical things, a lot of technicalities. Just to define these algebras of Cartan type, it takes some dozen of pages. Okay, so it's some very nice examples with algebras and so on, but okay, there are some, meaning there are some flags, and meaning those algebras of different meaning for series, the general, Hamiltonian, contact, and special. Yeah, they preserve some forms and yeah. Okay, so and then basically it was work of similar, yeah, classification. It's similar, yeah. It's less famous, and there was everything is less, yeah. There are less amount of people involved, less number of pages were written. But it's comparable, yeah, the same order of magnitude. Yeah, it was famous and people didn't go for this Fields medal. Okay, they published several papers in Annals of Mathematics, which again, honestly, it was like a matter of fact, yeah, because there are many people work and some people which did the final work, and many works were very similar to previous papers, yeah, but this some final classification efforts, yeah. But so it was a dozen of people, maybe less than 100, but something like that, yeah. And it took, meaning till recently, yeah. So it was, well, again, very similar classification of finite groups. Yeah, many papers was written, yeah, but of course there were some gaps, some mistakes, and there was some effort to somehow revise this and come with more like, you know, some second I don't know, second generation or something of this proof, but because still it's smaller, or maybe just good luck, there was one person, yeah, who did Helmut Strade, yeah, one of those people who just wrote 3 books, yeah, only 3, not like 10 or 20 or whatever, and in the final volume he appeared like maybe like 10 years ago, yeah, it was 3 volumes, classification of finite, something like that, yeah. On the final, and apparently there is consensus, yeah, everything it was checked, yeah, and it's also easy to check, yeah, because it's only 3 volumes, so it's like 100,000 pages. So this is right, yeah, but so it took like, I don't know, less than 100 years, but much more than heuristic 0. And so the final answer, okay, yes, it's Lie algebras of classical type, Lie algebras of Cartan type, in heuristic 5, Millikan type algebras. But only in starting from heuristic 5, yeah. Heuristic 2 and 3, it's more difficult, and it's open, yeah, it's open today. About heuristic 3, there are Meaning honestly, okay, so about heuristic 2 for some reason. Okay, start cooperating with some people. And heuristic 3, there are some people, they're optimistic. They will tell that probably there is some, they see the light at the end of the tunnel, and there are more or less, there are many papers defining, there are some theories which doesn't have counterparts in higher characteristic, and that's maybe the more or less complete list. Now we have to prove, yeah. And heuristic 2 is even not clear, so there are some very, and that somehow it gained started a lot of some activity, yeah, let's say, not maybe not a lot of activity, but in the last maybe 10 or 15 years, very different from different. There are very long and very interesting papers of latest and his sort of company, yeah, collaborators. And I think Andrei, yeah, you contributed to some of them, yeah. And basically their approaches were super algebras. Somehow in heuristic 2, somehow they show that you should take into super algebras into account, and to somehow they have some procedures to go back and forth, yeah, disparizations and so basically you should consider. And there are more like, you know, more maybe straightforward pedestrian approach, which is just trying to mimic, yeah, what was done in this generic characteristic, and how it works in generic characteristic. So basically, yeah, there is some, okay, in heuristic 0 we have Cartan subalgebras. It's one of the main two, yeah. So we have Cartan subalgebras, and then we consider root space decomposition with respect to Cartan subalgebra, and this root essentially, meaning somehow they behave, meaning Cartan subalgebras behave nice. It's not important. You just take one Cartan subalgebra and consider root space decomposition, and root also somehow you get very restrictive condition on those roots, and then basically you got Dinkin diagrams and goes down to some geometric, pretty much simple. Okay, so it's a simple geometric problem. There's some configuration of those roots, and we classify them. So it doesn't work as in positive characteristic. So instead, somehow Cartan subalgebras don't behave nice. Yeah, they can be of different dimensions, so they even the same dimension they conjugate with respect to automorphisms. They are not as useful. Yeah, it is some use. So instead of Cartan subalgebras, somehow people looking on what's called tori. Yeah. So it's more meaning it's okay. Basically the general idea it's more maybe the same, yeah. But somehow we take into account this P structure, yeah, which not necessarily exists, yeah. So there is the notion of restricted algebras of P algebras, yeah. So they have this raising into the power. So maybe raising in the power, of course, in Lie sense, yeah, not in a no such meaning. If you're raising in the power like verbatim, you don't get anything in the algebra, yeah. But it's sort of, it basically means that it's like multiplication, yeah. So if you consider operator of multiplying on some element, yeah, and then okay, so it's just operator, yeah, considering some associative envelope of this algebra, yeah, and you can raise it in the power in P, and if it happens that if you raise it and then it is multiplication on some other element, and this other element is called P power. Well, again, the formal definition is a little bit more involved, yeah, but it's more or less this, yeah. And you can consider what's called P envelope, yeah. So algebra is not restricted, but you consider some minimal restricted algebra, and then you have this operation which somehow, you know, some additional thing which you can play with, yeah, it helps. So you can see the Torah, it's basically okay, this is Torah element. Oops. Torah element, we just okay, so meaning if you're multiplying basically on it p times, yeah, it's the same, you just multiply once on this element. So they're semi-simple, obviously, yeah, because yes.
To the
yeah,
bracket
so maybe
power.
Maybe
can you write the definition? Yeah. On the left. Yeah.
Yeah.
So what? No. So what? So where should write? Yeah, what is the here? Or maybe I don't know. Here or the web. All right. So
Yeah, that somehow you you
Okay.
can you see that you can have to move and okay. You see that how you
No.
what you write.
honestly, I don't see because meaning I don't have glasses. But you tell me. So
Yeah.
can I write here or maybe I don't know. Here. Yeah. All right. So
Yeah.
so consider.
A little bit go to right. A little bit move to right. Yeah. Okay.
So where is the razor?
Because of course you can also control the moving part, but I don't know. Perfect.
Okay, so I will write
But
a little
can
bit. It will write here.
But bigger, yes.
It's fine.
Yeah.
All right, this is like by some historical reason. So this multiplication is denoted by add x. So it's basically multiplication. It's a joint, yeah. Operator. It's so y is okay from left from right. In characteristic 2, it doesn't matter, yeah. It's one benefit, yeah, in characteristic 2, but let's say on the right, yeah. And then you just consider its p power. You can consider this, yeah. So there's some operator. And it can happen, it may not, but it can happen that it's just multiplication on some other element, yeah. And this is what is called p power. And this is not always happens, yeah. But for example, this classical algebras, they're p algebras, but most of them, yeah. But with algebra, yeah, this is with algebra. We want say. From initially what was defined by bit, yeah. This is also P algebra. But some algebras
Here.
may not. But you can consider minimal P envelope and consider their tori, yeah. So this is also difference, yeah. So this is sort of sub-algebra, they're sub-algebras, yeah. And these toris are basically not necessarily sub-algebras in initial algebra, they're sub-algebras in P envelope, yeah. So we consider, and they are semi-simple, yeah, because if you have this condition, yeah. So basically they're annihilated by some variable polynomial. So that is semi-simple in just linear algebra sense, yeah. And you consider algebras of maximal dimension, yeah. Which is again sometimes it's not necessarily maximal sub-algebras, yeah, but algebras of maximal size, that's maximal dimension. Generally different things, yeah. But again, this is like the maximum dimension is sort of analog of rank, yeah, which rank in characteristic 0, it's like dimension of Catan sub-algebra, so the same, yeah. This the dimension of rank, and you try to cosify. So what is the program, yeah? Which more or less okay. If you try to mimic, yeah, this characteristic 0 approach, you cosify algebras of small rank. Which, well, in heuristic 0, it's not a necessary meaning. It's more or less you do classification right away, but it's more like it corresponds to the notion of what is algebra for rank 1 heuristic 0. It's L2 simple, yeah. And you have this important notion of L2 triples, and basically it's algebras which is isomorphic to L2, and somehow okay, so it's more like afterwards, yeah. But you can also use it in classification first to consider L2 triples and get and all this root system and so on. So if you first classify algebra small rank, but it turns out that you have to consider not algebras of rank 1, but algebras of rank 2 and maybe of higher rank. And then okay, so it sits inside, yeah, and then somehow you consider actually sort of representation of this algebra of small rank in this bigger ambient simple algebra, the structure you want to understand. And then okay, so somehow to do something, and so you need to first classify the algebra of small rank, and they basically build their representation theorem. And then yes.
Pasha,
So maybe I don't know if you don't use this, yeah.
Yeah, your phone is.
We consider very much is film is closed or not, yeah?
Yeah, sure. This is important. It's clear that if algebraically
Yeah,
close,
so you
you
don't consider anything like that here in characteristic because I don't see you say that you need a closed net algebraic.
yeah. So even we don't, so we have a lot of problems with algebraically closed field. Yeah, and in general, it's a tiny characteristic. Yeah, so you first specify object of algebraically closed field. It's obvious. Yeah, it helps a lot. Yeah. And then if you classify that, you try to, okay, if you want to classify arbitrary fields, you consider what's called forms, which you know very well. Yeah, it's like real forms. And then it's okay, some cohomology, but it's another, meaning another difficulties, another kind of stuff. Yeah. And so basically, and that's what people did. Yeah. And in heuristic zero, even in more general, the algebras of classical type of arbitrary. Well, perfect fields, of course, yeah, it's a perfectness, but sometimes over arbitrary fields and different, and but still there are some. Well, the forms are described in a sense, but what does it mean described? Up to associated, meaning up to description of division algebras. So basically, if you consider algebra of matrices, okay, SLN, yeah, its form is division algebra, for example. Okay, you take the commutator and you take a quotient by the center, yeah, because you have unit, it's one-dimensional center, yeah, and this form of SLN, center of simple, yeah, probably. But okay, so then we have some questions about division algebras, yeah, it's sort of, you know, Brouwer groups, and it's another kind of mathematics, yeah. And there are still some open questions, yeah, about the structure of such algebras, but then in a sense they classify it up to this associative way case, yeah, as to say.
Torian Cartan algebra.
No. Cartan, okay, characteristic zero and characteristic P,
Yeah.
something instead of that. No, it's not. We don't have any uniqueness or something. But
Conjugacy, I mean, surely.
it's like more or less like you okay. So you have algebra for rank 1, yeah. It's where you have this
Yes.
maximal.
Only
You have a
rank 1.
maximal the
Yeah, okay,
tori, and by the way, it happens that they not exist, and that's what I want to tell. It's very. It's something very obvious, yeah. Just but. Something very counterintuitive. The first example, yeah, three-dimensional simple, is an SL2, yeah, because you take verbatim SL2, it will be nilpotent, yeah, in heuristic 2, yeah, because algebras of 2 by 2, it already shows, yeah, the weird things happens, yeah. You ask why meaning it's just no, it's heuristic 2, yeah, it's not as a general positive heuristic, but okay, so you can take you can remove the artificially this coefficient 2, yeah, into simple algebra with just multiplication, yeah. We don't have signs, but it's of rank 2, it's not of rank 1. It's not P algebra, it has P envelope of dimension 5. So basically those you can add those elements, yeah. Dimension, so to initial basis, and you have two additional dimension 5, and this is torus, yeah, and you don't have torus of rank 1. Moreover, there is the theorem of Skrabin, yeah, it's one of the papers which Skrabin, yeah, he contributed a lot some time ago to this, some understanding and advancement, yeah, in this small characteristic that there is no in heuristic 2, there are no meaning this minimal possible rank is 2, yeah, for simple algebra, it's not 1. So it's already you should consider algebras of higher rank, and somehow people understood, yeah. So the small characteristic, the algebras, this initial step, yeah, to describe algebra small rank, we have to consider algebras, maybe heuristic 3 algebras of rank 2 and 3, and characteristic 2 maybe up 4, who knows, yeah, something like that, yeah. So what no, it's just some not. All right. So, but in general, okay. So heuristic 2 actually is a crazy word. Yeah. If you start to do things, yeah, you don't have signs. It's good, but otherwise everything is different. Yeah. You have. And actually, it's difficult if you switch that to normal, you know, the normal sort of word. Yeah. It's sort of, you should somehow to make mental effort. Yeah. not to make some just to get used to it. Yeah, so but basically let me continue with this specific more or less straight specification effort, yeah, which we tried to follow, yeah, with my co-authors and some other people. They just okay, so mimic general characteristics. So then you have basically in many places a lot of you consider some filtrations, yeah, with respect to some maximal subalgebra, something like that, yeah, and you somehow naturally should consider a problem of the description of filter, and you have a filtration. You can consider associated graded algebra, which usually somehow simplify the structure, yeah, and then you should go back, and so you should consider a problem of description of filtered algebras, which whose associated graded algebra and such, yeah, and this is deformation, basically described in terms of deformation. Which you basically don't have such, meaning again you have such, you may see what you have in heuristic zero, but basically it's very quickly, yeah, you don't get anything difficult. Basically it's not explicit there, yeah. So the heuristic P, you have some examples, yeah, some non-trivial examples, and again you have these roots, but it's more complicated. It's not just, you don't have anything like Dynkin diagram. Okay, you have definitely Dynkin diagrams in the quasi-algebra classical type, almost, yeah, the same, but otherwise, yeah, you don't have such nice structure. But so again, so just algebra, first step algebra of small rank, yeah, and that's what we did. Okay, so basically there was some previous work. And that's what we try to advance a little bit, yeah. So, oops. Yeah, some time ago again, my co-author, very technical. That's what we did essentially. I was different here. It looks and sounds very technical, yeah. It's even not just algebra of absolute. Okay, absolute Toro rank. Basically, this is Toro rank, yeah. But absolute, yeah. But there is some relative Toro rank. If you have some subalgebra, you consider tori, which sit in this subalgebra, and somehow Cartan subalgebra also appears. Yeah, I don't have to, but still there are some use, but not of such use. So this, yeah, so simple algebra rank 2 with this additional condition, Cartan subalgebra of Toro rank 1. Yeah. And actually, the answer, and it was some small step, yeah, to move. So basically, there was again this previous work of Skraben. He described this, but again up to this filtered deformation. Yeah, so essentially what we did, we computed some filtered deformation, and this is basically filtered deformations of this algebra. Yeah, and what I said, yeah, this is semisimple algebra. In characteristic 2, it looks again. So what was the structure of this algebra? We have simple. So maybe I will just. We have simple algebra. This is just this 3-dimensional. Yeah, from the previous slide. This is what is called reduced polynomial algebra. Some it's 4-dimensional. Some very particular case. So basically, it's like polynomials in 2 variables. Module what? No. Okay, so it's but okay, it's isomorphic. Yeah, I can see the polynomials 2 variables. Modular squares, yeah, so it's something, but so it's like divided powers. It's something isomorphic, but with different representation. Yeah.
For me, that's a deformation. That usually means that you have.
I will come to that. Yeah, what is deformation? Yeah, it's ambiguous. Yeah, it's overloaded word. Yeah, but it's something very, very concrete. And again, very over again it happens. Yeah, it's allowed to work. And this is like I said, this is derivation tail. Yeah, so both those two things. Like okay, derivation of this part. Yeah, this is this from P envelope, but it's clear that any element from P envelope is derivation of algebra. Yeah, because it just power P power. Okay, so it's almost it's one of the first exercise we learn the algebras. Yeah, if you have derivation in heuristic P, it's P power without a derivation. It's easy to check. Yeah. So any P power of inner derivation of this adjoint, it will be also derivation. It's not necessarily maybe of such, but it is derivation. So this is derivation, and this is just okay, and this is just multiplication on those this algebra. So basically, these things acts like derivation here, and just multiplication here, and this derivation of this tensor product. And the structure of this tensor product is just straightforward, just factor wise. Yeah, you multiply elements here, multiply elements here separately. So basically, it's like in general, yeah, this is my favorite topic currently. Yeah, from physics, algebras, you can take any algebra, tensored with associative commutative algebra, and it's algebra. And this is like what is like this derivation. It's like it's analog of usual derivation. Yeah, it's like for some reason it's in some cases you can see that instead of this reduced polynomial divided powers. Basically, multiplication is more complicated, and derivation is just overs the degree without any coefficients. It is isomorphic. It's a little bit non-trivial isomorphism, but it's somehow sometimes it's more beneficial to consider. So this is semi-simple. Yeah, it looks like some weird construction and some very, but it's actually very typical. Yeah, typical kind of construction in this work of algebras in general in positive. It's like I mentioned, this Bock theorem. It's more or less like what is how the typical semi-simple algebra looks like, unless it's not direct sum of simples. Yeah. Well, it can be direct sum of maybe direct sum of such things, or it may be something more complicated, something sandwiches between this and this, but more or less this is what additional shows the additional complexity. Yeah, also when we talk about semi-simple algebra. So and we had to compute the filtered deformations. What the filtered deformations? What I said exactly. Yeah. Okay. Formally, it has nothing initially has nothing to do with deformations. Yeah. You have some filtration. You can you have some abstract algebra with some filtration. You can see the associated graded algebra. And this associated graded algebra is more to this, and here grading something grading by this. And wait, it's more honestly I forgot exactly what. So definitely it's like graded by this, and probably this also meaning something. So basically, okay, so in general, it's not necessarily with the algebras, yeah, but associative algebras, any kind of algebra, this is sort of natural problem which sometimes arises naturally, yeah, in this classification business. You have to consider filtered algebras described, yeah, whose associated graded algebras are of given type or isomorphic to given algebra. But it's immediate, yeah, it's from classical work from Gerstenhaber, yeah, from the algebraic deformation theory from 60s. Basically, you can describe in terms of deformations in formal sense, yeah. And what is deformation in formal sense in Gerstenhaber? You consider sort of, you have initial algebra, and now you consider sort of formal power series, and so initial term your multiplication, and then you have additional terms with powers of t, one parameter, or it can be some more complicated several parameters. Yeah, absolutely formally. Yeah, and then it's important. Yeah, you do this within some variety. Variety meaning defined by identities like Jacobi. So you have algebras, associative algebra, whatever. And then it turns out that if you do that, so those initial terms, they have the interpreted in terms of cohomology. Yeah. So this first term is exactly we give cycles, and then you have some natural equivalence, yeah, with some again power series, and this equivalence exactly give you co-boundaries. So essentially, the first term in deformation is described in terms of second degree cohomology in adjoint modular in algebra itself. The same for associative algebras, and that's it basically for this classical. Yeah, you can frame it like this. It happens if you have some good developed cohomology theory, like classical cohomology theory, then deformations are described in this cohomology. Yeah? And all subsequent terms they basically give you abstraction, meaning they describe in sort of equations. So you have differential of the subsequent terms, they equal to something which can be understood like as abstraction, and it's twice in the third cohomology. So basically, to describe deformations, you have to compute this, according to this scheme. Yeah. Second cohomology, third cohomology, strictly necessarily you don't have to describe. Yeah, because then you have to compute what's called massive bracket sometimes of these cocycles. yeah, and then if they zero, that's okay. You don't have abstraction. If they not zero, you have abstraction. But they already something which we live in their cohomology. It's nice. You can compute. You can somehow to put all this together. But strictly speaking, not necessarily compute third cohomology, which is more difficult second. And that's it. Yeah. So well, more or less, yeah. There are 4 papers against the Haber, annals of mathematics, but essentially that's it. Yeah. And okay, so we did that, yeah, and
forms for this finite dimensional Scriabin algebra. How many different Z gradients do you have? Because you know, if you change the grading,
I don't know.
Because if you change the grading, you
Maybe difficult question, yeah, because gradings are difficult to describe.
Yeah, because when you change the gradient, you have a different filtering.
Yeah,
forms.
sure. I understand why you asked me, yeah, because it's one of the topics you consider the latest. I don't know. I really don't know. And actually, we didn't, but because so we wanted to solve this problem, yeah. And okay, so for that we have to compute this concrete, yeah, this classic sort of more or less very natural grading, yeah. Obviously, it has some other grade. I will talk a little bit about gradings and some other algebras, but generally it's a difficult question. Well, and this is what we got, yeah. So it's what this is algebra, yeah. This algebra 15. This algebra is 15-dimensional, yeah, 15-dimensional. So it's 3, 4, 3 times 4, 12, 3, right? No, 12, 1, 2, and 2, 1, yeah. 15-dimensional. So the deformation is 15-dimensional, and we have okay. This is two parametric, yeah. We go to parametric deformation. And this multiplication table, which is a little bit crazy, but somehow we learn to work with it, yeah. And what is interesting, yeah. It's 2 parametric deformation, but it's still a deformation, yeah, by some two cocycles which are not non-trivial, yeah. But it turns out that all algebras are isomorphic, yeah. And this one of recently it's one of so last year's one of the favorite topics of again Latest and his company, yeah. And actually this is there. And honestly, this is thanks to them we understood indeed that this is what is the case, yeah. So we somehow proved with ad hoc. Initially we didn't know, yeah. Even meaning in that paper, yeah, in 2015, when I mentioned, we just pulled the question, we don't know. It's complicated, yeah. If you look on the question table, how to decide, but it turns out that it's relatively easy with some ad hoc isomorphisms, yeah. But then when there is phenomenon, yeah, which is was somehow it's not for the first time they discovered it. Was known earlier, but different contexts, even maybe. I'm not sure about heuristic zero, but heuristic zero definitely not simple algebra. Some I don't know, semi-direct product or something. But it seems there is something important. Yeah, this phenomena. It happens again and again in small characteristics. So you have non-trivial cocycles, yeah, which prolong. Yeah, to the full deformation. But at the end, it turns out that somehow, for some ad hoc reason, yeah, all the deformations are isomorphic. So initially, cocycles are non-trivial, but they lead to actually they don't give you anything. If you're interested after isomorphism, yeah, to want to describe this algebra. And this is a question which again was posed by Latest, maybe not once. Okay, Latest and his collaborators, maybe not once in some recent papers, how to describe the situation, yeah, in cohomological terms. Yeah, it's not very clear. Meaning it can help a lot. Basically, because if you compute it, actually. Again, Latest with his collaborators, they did a lot of computation on compute with help of computer of its low degree cohomology of different kind of algebras. Yeah, they're big and it's complicated, and somehow I don't know, it looks terrible sometimes. But it often happens that those different meaning, and that you can deform with help of all this. to cocycles, yeah. But it happens often that that deformation is semi-trivial. But again, just ad hoc, yeah. You somehow you realize that, yeah, afterwards, yeah. So the question, so somehow to try to detect on the somehow the way of cohomology, yeah. So what if you have some cocycles? How you can tell, yeah, whether without doing really writing and some finding this isomorphism, how you can tell whether it leads to semi-trivial deformation or not? It's open question. It sounds simple, yeah. So but again, it's basically about this Gerstenhaber theory class, which honestly the simple theory. It's very useful, nice, but it's simple. Okay, nowadays they're clever, yeah. It's 50, 60 years afterwards, yeah. It's simple theory, but not very clear. And if we were able to answer this question, it will help a lot, yeah, in this business. All right, so there is one of these phenomena which happens often, yeah, which I wrote in abstract. Yeah, they have some peculiar properties. In this case, it's not peculiar in a sense. This is sort of what happens, yeah, often. Well, and then okay, so but then okay, so this algebra, yeah. But what I want to say, so I somehow sorry, I'm just maybe moving too fast. Basically, this algebra in our paper 2015 comes as outcome of this computation. Basically, it was not necessary to consider it, yeah, because the answer to this basically description, yeah, is pretty much boring and simple. Only three-dimensional. This S, yeah, which is only three-dimensional algebra. Boring and simple, but useful, yeah, to advance further, yeah. And this algebra just came. Like basically, it boils down to we compute the deformations. We got this parametric family, and that at that time we didn't understood that this is just all algebras isomorphic. But we understood that this rank is bigger than meaning it doesn't satisfy those conditions. Yeah, so it was thrown out. Meaning not exactly okay. So we said maybe algebra is for to investigate. Yeah, what we did. Yeah, recently in this 2020, 22. Yeah, just recent paper. But at the time, well, it was not for this classification. It was not. So all right, so it's about this algebra. So what we did in the recent paper, we just dissected it, yeah, as much as possible. It just looks like we took the what's happening today, yeah, when people interested in this classification characteristic too. In some sense, the situation is similar to 50th or 20th century in generic arbitrary positive characteristic. New and new papers appear with titles a new simple algebra of contact type of some, I don't know, something alternating Hamiltonian or whatever in characteristic 2. And it is absolutely, and they're defining something. It's absolutely not clear whether it's indeed a new, because there is no list. Okay, there are a bunch of papers, and there is some wild zoo, yeah, and it's not clear what is new, what is not. And there is no some conjecture, yeah, what should be the list. And okay, some people like Jacobson, maybe less famous, but they're pessimistic. They're saying, well, it's a wild, and I'm optimistic. Yeah, I think it will be very technical, but we were able to classify. I don't know when. Yeah, actually, there are no light at the end of the tunnel. Characteristic 2 definitely not. So maybe later we will not agree, but again, he thinks in different terms. Yeah. He formulated, okay, we should take some deformation. We should take all possible analogs of this Cartan type algebras and their derivatives, and consider all possible deformations and derivations and again deformations. But well, that's good. But so we should do that. Yeah, in a sense, people. But it's probably it will be a huge list. Yeah, and it doesn't help much when you have a new paper. Yeah, but when you know new alternating Hamiltonian whatever, but it is there or not. Yeah. So yeah, so we took this 15-dimensional. Okay, so you can assume, meaning they're all those two coefficients, which for some reason I don't remember the beta and delta. Okay, you can assume that zero. Simplifies a bit, yeah, this multiplication table. So we dissected this algebra, yeah, which seems a little bit strange. Yeah, we have a lot of algebras, yeah, we just took this algebra and just said as much as possible about it. Yeah, what we did. But actually, it was I don't know whether if you look on the paper, if it's clear or not, we were little bit, we had some ambition, yeah, which maybe was not set, yeah, and described in this paper. Explicitly, we tried to set a way how this should be investigated, yeah, in order to somehow to tame this zoo, yeah, how those exotic and crazy, I don't know, multiple examples should be investigated, yeah. So properties, yeah, again, some cohomological properties, but again, it's like, because I somehow emphasized about cohomology, because this seminar, it's cohomology in everywhere, yeah, but okay, this is why some, it's not like cohomological algebra, yeah. So basically we're concerned about this low degree cohomology, which is important, yeah, from the structural viewpoint, like deformations, okay, central extensions, which are also sometimes important, extensions of modulus, I don't know what else, basically derivation, the first cohomology. So also meaning it's good to compute them to have some invariance, yeah, when you decide whether algebra is isomorphic or not. Well, of course, how you can decide? You look on some invariance, and well, something doesn't match, good, they're not isomorphic. But the bad thing that in many cases everything matches, yeah, and then it's something else. So meaning we computed, and okay, part of this computation were done, big part maybe on computer using gap, not mathematical, not the super early package which latest is using. Somehow it's pity, yeah, but they are very powerful. But you should be there, yeah, you should be in just in their team to be able to use it, yeah. It's I don't know, I'm using gap, and well, this is properties, yeah. Okay, absolute error rank is 4, yeah, it's 4 on this 15-dimensional algebra. So probably the OP, like I said, it seems like you have to describe algebras at least up to rank 4. So it should appear somewhere in this future classification of algebra rank 4 probably. Okay, subalgebras, yeah, what of subalgebras? Computed automorphism is probably the most complete meaning. So sort of all this is more or less linear algebra, yeah. You know, degree cohomology, automorphism with some okay, so some algebraic groups, and yeah.
So that this 15-dimensional Scriabin algebra has no analog with the algebra in zero characteristic.
No, not absolutely not. Like, you know, it's even worse. Yeah, it doesn't have analogs in positive, in generic positive characteristic, like many of those algebras. Yeah, and about gradings. Yeah, we discovered a lot of gradings, but somehow we were unable. Meaning, well, it was not the meaning. Probably if we would put such goal, yeah, we would classify all the gradings, but it's difficult. Yeah. You have some schemes, of course, it's related to automorphisms, yeah, but still, and some, you can. There are some theorems which allow you. I think this is one of your papers, yeah, exactly. Which, but it's under some condition, yeah. You can describe gradings, not all gradings, yeah. It's basically, yeah. So,
you can construct.
Okay, so your paper, but at least okay. So among other things about Z2 gradings. All right, Z2 gradings, even Z2 gradings are non-trivial, yeah. So maybe this is the most simple, like Z2, yeah. It's non-trivial, yeah. The whole meaning the paper with Andre and some other people, yeah. But yeah, and of course this is interesting, yeah, to describe gradings, yeah. And it's a sort of also sort of, you can consider sort of invariant, yeah. And yeah, interesting thing, yeah. So now it's not about cohomology, about some computers, calculations, and some time ago there was a paper of Ike, yeah, and Ike she's a big expert in computer algebra, and mainly she's not working in algebras, mainly in groups, finite groups. And really, meaning she is very meaning she's devising very clever algorithms, yeah, which working in a very efficient way. And she got interested somehow at a certain point about how to do algebras. So somebody told her, okay, there is some, you know, thing which you can apply your skills in group from group theory to Laugen characteristic 2. And she produced a list of all, meaning what was written here, of course on computer, yeah, on computer you work on some concrete fields, yeah, and okay, GF2 is natural characteristic 2, and she produced out of dimension up to 20. She does not claim that it's a full list, yeah, because she used randomized, so she somehow she has some method to generate to construct those algebras, basically considering them algebras in some bigger algebras, and then it was difficult part to decide what is isomorphic or not, yeah, because well, it's a non-linear problem, yeah, it's quadratic equations, so it's system of quadratic equations, which, well, in general you don't have algorithm. You can try a lot of things, it's very interesting, yeah, but and also she has some very clever way to decide, but basically produced that list. She didn't, because those algorithms were randomized, yeah, how she produced algebras, yeah. So many times she tried that, and then it was a list. And it turned out that this list is not complete, yeah. It was not again it's complete, but it's what sort of surprise, I would say. Yeah, so and actually, one of the ways, somehow again, it's not something very clever. If you think it's just something very straightforward, but apparently it was not right. Yeah. So somehow we realized that when you're deciding about isomorphism of those algebras, yeah, and so you sometimes it's just beneficial to look on. It's about just number, yeah, some number. Okay, of GF2 you consider, yeah, some number of subalgebras with that and that properties, yeah, which apparently was new idea, yeah, which is pretty much pedestrian idea, yeah. But okay, so you can try a lot of things, yeah. That's the point. Something works. But really, we work a lot with this algebra and tried, okay, to compare it to algebras in Ike list and so on, yeah. So really, just do this. It's like some crazy number. Okay, in that paper, we have some 17,000 something subalgebras of dimension 7 with such and such properties, yeah. Well, and in other algebras you have 20,000, yeah. So those algebras. All right. So okay. So this is what sort of surprise, and yeah, I think that this point I will finish. So about this some peculiar algebra, yeah. But there are a lot of maybe this is sorry. Yeah, just okay. So what there are a lot of work. Okay. The main problem is to classify algebras, simple algebras, characteristic 2. But who knows when it will finish? Maybe not in our lifetime, but who knows? Yeah. Unless something, but meaning what you can try to do again, somewhat to some degree to mimic, yeah, what was happening in generic characteristics, to classify those algebras under some restrictions, yeah. For the algebras, so we observed, this, for example, this algebras have very peculiar grading, what we call thin. So basically, it's just grading. Grading where each component, so you have some tori for dimensional in this case, and one which is outside, completely outside algebra. So it can be partially, so generally it's in envelope. This algebra is 19-dimensional envelope, so it has 4-dimensional torus, which completely outside, yeah. And with respect to this torus, it has the composition 15, which parameterized by G60, like GF2 in the power 4 minus 0 minus zeros, yeah. So with the one dimensional, with very particular, kind of grading. So it's basically that, and we call it, and somehow we got a feeling that it's very restrictive, of course, but so it somehow is important, yeah, to consider such algebras and to study this phenomenon. We call it thin decomposition. Yeah, and it could be that so first we classify algebras with this thin decomposition, and then we will consider maybe it could be, yeah, so it will be deviation. So it's not just algebra of small rank, but algebra with some additional, and then with they're sitting inside this ambient algebras, it somehow can. So there is a lot of questions, in this paper and some of the technical characters. So well, and that's it, yeah.
Thank you very much.
Yeah.
But among us here.
I think so, yes.
Yeah.
But yeah.
You have some Z2 gradings, right?
Yeah. Yes, of course we have the two grades of that algebra, and we haven't tried. Meaning, almost somehow I don't know. Honestly, right now I cannot answer why we haven't applied your method. We haven't, yeah. So it can be done, or definitely, yeah, but.
But even about not about that method, but have you tried to? You have some Z grading. You can superize it by method 2 from.
Yeah. No, we haven't tried that. Yeah. So, but actually, it's now even I don't know, but definitely it's one of the things which is worth trying. See what.
Okay, and the second question: how you know that it's different from these IK algebras?
Okay, so basically just we compute, but if you compute this a lot of things here the same, yeah. It's actually, and we already we did that like in this paper of 2015, and we computed, okay, this what backs up cohomology and sandwich subalgebra and derivation algebra and what else, yeah, and all the same, yeah, for almost all this out 15-dimensional algebra in IK list, it's all the same, so we're not sure. Yeah, and but it's about this subalgebras, yeah. It's about basically it's simple. It's seven-dimensional subalgebras. It's all there is some paper of Grishkov with these Brazilian students. They describe seven-dimensional simple algebras or heuristic two algebraical field. The author of House is called basically some generalization of with algebra, of the algebra of general Cartan type or Hamiltonian, yeah. And so we just computed some number of some algebras, and it is pretty much meaning it's some few dozens of seconds per algebra, yeah. It pretty without any efforts to optimize it, just to some. So it's pretty much quick, yeah. And it works, yeah, in this case. So this equation, you a priori you don't know, yeah, what to use, and if you want to compute to prove that the algebra is non-isomorphic, yeah, and then you should find what is appropriate.
Yeah. And maybe last one.
Oh well, yeah, meaning could be. Yeah, you probably you know better than me. I don't know. I read a lot of papers of Latest and his company, but I don't have a good feeling about this meaning. It could be, yeah, but probably you know better. Yeah.
Pasha, I am here. Yes.
Surprise.
Well, may I ask a question?
Sure. Yeah.
Well, I wrote a paper to you and to Andrei speaking about gradings. Well, that's not a question, that's rather the answer. I'm not sure that it is interesting to consider all gradings, but certainly some of the gradings are definitely of interest. And if the algebra is totally weird, I mean exceptional, then I don't know which gradings should be considered as interesting. But if you can include your algebra, and this is the case of the algebra you're considering, well, you can include it into a series labeled by a shearing vector, and you can shearing vector of heights of some indeterminates. And some of these heights can be equal to infinity. Okay, let all such heights be equal to infinity. Consider this infinite dimensional algebra and consider its Weisfeiler gradings. These are definitely of interest. And then shrink your shearing vector to consider your particular finite dimensional algebra. for them, for these gradings, to consider filtered deformations is, it seems, much more reasonable and more interesting problem than for an arbitrary grading. But okay, as I said, that was answer, not a question. My question was, could you please, maybe not right now, but just send me a letter. I know what is sandwich subalgebra if characteristic is distinct from 2, but what is
Yes.
this?
But it's okay, yeah. I think it's almost the same. Yeah, but there is some differences which honestly I don't remember. But it's written in the paper. Yeah, it's like, no, I do not tell you. It's just generated by. No, I think you can. If the thing is, as far as I remember, is you can take the formal definition like in generic P, but just one of those conditions will be redundant. Yeah, so you have square 0 elements, and then the sandwiches, meaning basically sandwiches, AX, meaning this condition. One of them is redundant, something like that. Yeah, but
Pasha, I didn't want to press you right now because it's difficult to answer on the spot in front of the blackboard or whiteboard. The answer is in the paper, right?
Yeah, sure. But
Well, I'm sorry, I missed it.
Okay, but I could, I can write you.
That's it.
Because I remember indeed it was like when we discussed this with Grishkov, it was raised, yeah. So we should be careful with definition of sandwich subalgebra characteristic 2. So that's true, yeah. But
since you're talking about classifying things in somehow low rank dimension or whatever quantity you want to measure it with, is there some kind of online list that you can consult with, or do you always have to dig in literature?
I was saying.
I mean, like of the things that have been discovered so far. Like,
no. That's the point. Yeah.
Okay, so there's no systematic collection.
Stage, yeah.
Not
Somebody
yet.
on the level of Kostrikin and Shafarevich should came, or and just it should be some scheme, which is okay. So some again, Mita and his collaborators are moving in this direction, but still it's far from that. Yeah, it's like some ideas how it should, but there is no list. Yeah, and that's the point. Yeah, you cannot check. So new paper with appears now and then. Yeah, new example again.
Okay.
It's absolutely chaotic, as I see it. Absolutely, right now it's chaotic state. Yeah, but it doesn't preclude you to move slowly. Yeah, in the amount, meaning in the midst of this house. Yeah, to just advance little by little with these small ranks, and then do part of this house somehow we will understand. Yeah. But of course, it will help exactly what you're saying. But it's not problem.
I have last question because I have cleared in algebra. So there is some motivation.
So I don't know quite. So no. He had gotten just wrote a paper in some in 1998 or something like that. A very long again technical paper. Very advanced. So basically, he proved. And basically, the algebra with 0, meaning it appeared what exactly like the node 0. It appeared there. Yeah. So it's some meaning what I said, yeah, among other things, yeah, the paper very rich in content, but he just described those what we did, yeah, but up to some filter deformation. But he didn't compute those filter deformation. Well, it's some work, yeah. If you did some 20 pages, cohomology, and we did it with some little bit more general, some tensor products, some interesting formulas. So that's interesting. But basically, what he did is he described up to filter deformations, and he gave example, yeah, one of those deformations, yeah, and more or less we proved that that's it, yeah. So that we don't. Okay, so in that paper we proved that we have to parametric family, but now it turns out that we don't have anything new. So compared to this example to describe an algebra. And actually he has examples in high 15 dimensions, the whole series, yeah? It's 15 dimension with the most smallest. It's of dimension 2 in the power something, and I don't remember, yeah? So where here you have something, no, not 2, but something like that.
Okay, so let us thank the speaker again, yeah?
Yeah.